In this video, we're going to talk about how to evaluate limits graphically. Imagine someone is standing 10 meters from a wall. We tell that person to move halfway to the wall. We then tell them to move again halfway to the wall. And then we tell them to do it again halfway to the wall, and we continue to do this. Theoretically, the person will never reach the wall. However, we can say that as the number of trials moves to infinity, the limit of where the person's standing will be the wall. Of course, the person will never reach it theoretically, but we still refer to the wall as the limit. So we don't say the limit approaches the wall, we say the limit is the wall. Another way to think about limits is to think about sequences. Consider the sequence f of n, where n is a positive integer referring to the ordinal position of the term in the sequence, and f of n is the value of that term. So we see here that when n is 1, f of n is 1. When n is 2, f of n is a half. When n is 3, f of n is a quarter. When n is 4, f of n is an eighth, etc. We see that the numbers are getting closer to 0, so we can say that the limit as n goes to infinity of the sequence is equal to 0. Even though it'll never reach 0, the limit equals 0. In mathematics, a limit is the value that a function or sequence approaches as the input or index approaches some value. Limits are essential to calculus and mathematical analysis in general, and are used to define continuity, derivatives, and integrals. When dealing with functions, we can let the x value inputted to the function grow closer and closer to some set value. We then watch the pattern of y values to see if there's a set y value that we grow infinitely close to. If there is such a value, we say that that is the value of the limit. So suppose we wanted to determine the limit as x goes to 3 of the function negative x squared plus 6x minus 5. Let's do this by graphing y equals negative x squared plus 6x minus 5. Using our grade 10 methods, we recognize that we have a quadratic, and we can complete the square, put it in vertex form, and we have the expression shown at the bottom. Now, that will be a parabola with a vertex at 3, 4, and it will open down. To determine the limit graphically, we're going to approach an x value of 3 from the right side and from the left side and see where the y value is heading. In this analysis, we're never actually going to arrive at an x value of 3. We're just going to approach that x value of 3. So let's approach an x value of 3 from the left-hand side. If we start at an x value of 1, the y value is 0, shown by the red dot. If we go to an x value of 2, the y value is 3. As we go to an x value of 2.5, the y value is 3.75. At an x value of 2.9, the y value is 3.99. So we're starting to get a feeling, yeah, I think we're getting close to 4 here. At an x value of 2.99, the y value will be 3.9999. Boy, are we ever getting close to 4. It looks to us like as we approach the x value of 3 from the left-hand side, we can see the y value is approaching 4. Now you might say, well, it's also approaching 5, but not really, because the number that we're getting infinitely close to is 4. We're not getting infinitely close to 5, but if we keep on pushing the x value close and close to 3, our y value will keep on getting infinitely close to 4. Now, there is a more thorough definition of limits that your first year university professor will share with you, but for now, we're going to use this conceptual idea. Well, what we can say is, as x goes to 3 from the left, we write it this way, the limit as x goes to 3 from the left of this expression equals whatever the y value is that we're getting infinitely close to. Now that's called a one-sided limit. We still have more work to do to evaluate the limit as x goes to 3 overall. We've evaluated the limit as x goes to 3 from the left with that minus sign there. Now let's evaluate the limit as x goes to 3 from the right. Okay, so at an x value of 5, the y value is 0. At an x value of 4, the y value is 3. At an x value of 3.5, the y value is 3.75. And just like last time, as we get closer and closer to 3, the y value gets closer and closer to 4. At an x value extremely close to 3, the y value is extremely close to 4. It'll get infinitely close to 4. It won't get infinitely close to 5 or 6 or some other number, but it will get infinitely close to 4. So we can see intuitively that as we approach an x value of 3 from the right-hand side, the y value is approaching 4. Okay, so we can write that expression right there. And that's also a one-sided limit. Now, the x-coordinate we can only arrive from the left and from the right. There are only two ways to approach it. And so what we can say is the limit of the function as x approaches 3 from the left and the limit of the function as x approaches 3 from the right need to be compared. So if the limit as x approaches 3 from the left of the function exists, and if the limit as x approaches 3 from the right of the function exists, and if those two one-sided limits equal each other, then we say that the limit as x approaches 3 with no qualification of from the left or from the right, we say that it exists and is equal to that common value. So in other words, since both of those one-sided limits equal 4, we say the limit as x goes to 3 of the expression is equal to 4. In other words, when determining whether the limit as x approaches a particular value of a function exists, we compare the two one-sided limits and see if they're the same. If they are, then the limit exists and is equal to that common value. So here's our statement of O limits that's worth remembering, highlighting. If the limit as x goes to a from the left of f of x equals b, and the limit as x goes to a from the right of f of x equals b, then the limit as x goes to a of f of x equals b. However, if one of the one-sided limits exists and the other one-sided limit exists, but those two one-sided limits don't equal each other, then the limit as x goes to a of f of x does not exist. And that'll happen to us. So let's consider the next function. We're going to use a graphing approach to evaluate the limit as x goes to -2 of f of x, where f of x is equal to the quotient shown. And or we're going to justify that it doesn't exist. Well, using our skills from grade 11 and 12 math, we see that what we really have here is the function x plus 1 with the restriction that x cannot equal -2, because we're able to cross out those common factors. Okay, so we have a function that looks like this. Now what we're going to do is we're going to approach from the left. Now, as we approach an x value of -2, as we approach it from the left, we see that our y value, as we keep getting closer to an x value of -2, our y value gets infinitely close to a value of -1, so we can make this one-sided limit statement. And similarly, from the right, we can make the same one-sided limit statement. Now remember, the key word is approaches. We're saying what's the limit as x approaches -2 from the right. We're not saying we arrive at -2. We're saying as we approach -2. And the answer is -1. Okay, we don't actually arrive there, but we're getting closer and closer to that value. So the limit of f of x as x approaches -2 from the left equals the limit of f of x as x approaches -2 from the right. That means the limit as x approaches -2 of the function f of x exists and is equal to that common value. So in other words, since the limit as x goes to -2 from the left, and this little negative sign there, and that superscript, that indicates from the left, and this little positive sign in the superscript indicates from the right. And since these two values each equal -1 and they equal each other, since both values equal -1, we can say that the limit as x goes to -2 of f of x equals -1. But when using a graphing approach, we have to consider that left both from the left and from the right as shown above on this same slide. So the lesson to be learned from this example is that it's possible for a function to be undefined at a particular x value, but for the limit of that function as x approaches that value to exist. So in other words, when x equals -2, the function doesn't exist, but the limit as x goes to -2 of this function does exist. In fact, this is a very common occurrence when we get to algebraically evaluating limits. When we get to algebraically evaluating limits, where we're going to spend a lot of time in this unit, that is going to be an extremely common occurrence, what you just see there. Now, what if we're given a piecewise function? F of x equals the rational function shown earlier if x doesn't equal -2, but f of x equals 3 if x does equal -2. Well, we're going to use a graphing approach to see if the limit exists. Well, as we saw earlier, this function right here, we saw it in our last example, looks like the straight line you see on the board, but with a hole. And f of x equals 3 when x equals -2 is just this point. Okay. Now, as we approach from the left, the limit as x goes to -2 from the left is equal to -1. We don't arrive at -2, we only approach -2 from the left. And as we get infinitely close to -2 without arriving at an x value of -2, our y value gets infinitely close to -1. So that's our one-sided limit. Note that we're looking not at the value of the function at x equals -2, rather we're looking at the values of y as x approaches -2 from the left. As x approaches -2 from the left, the values of y go from -2 to -1.1 to -1.01 to -1.0001, etc. This pattern leads us to -1. It doesn't lead us to 3. As we're approaching, we're never getting infinitely close to 3 following the y values we get as x is approaching -2 from the left. These y values, not when we're at -2, but when we approach -2 from the left, those y values aren't getting close to 3. That's kind of like an anomaly. Now, we are going to approach from the right. We see using a very similar analysis that the limit as x goes to -2 from the right of f of x equals -1. Again, if we're following along here and we're following the pattern established as we're approaching -2, as we're getting infinitely close to an x value of -2 and approaching from the right-hand side, we see that this pattern established when x is approaching -2 gets our y value infinitely close to -1. We don't arrive at an x value of -2. So we only look at the pattern established as we're approaching it, and that pattern leads us to a y value of -1. Okay, so we're not looking at the value of the function at x equals -2, rather we're looking at the values of y as x approaches -2 from the right. As x approaches -2 from the right, we see that our values keep getting closer and closer to -1, not to 3. And from these examples, we see that the limit of the function as x approaches -2 from the left equals the limit of the function as x approaches -2 from the right. Therefore, the limit of the function as x approaches -2 is equal to that common value. They equal each other, as shown here, the limit from the left and the limit from the right, and they both equal -1. So therefore, we can make this grand statement here. Now, the lesson to be learned from this example is that sometimes a particular function has a particular value at a given value of x, but oddly enough, the limit of that function as x approaches that x value is different. So in this case, f of -2 is definitely 3, but the limit as x goes to -2 of f of x is equal to -1. Strange indeed. Now, what if we have the piecewise function shown here? Okay, well, first we'll graph the function y equals -x minus 3, but only the part to the left of and including -1. And then we will graph the function y equals 3x, but only the part to the right of -1. And we have the function as shown there. Now, as x is approaching -1 from the left, our y value gets infinitely close to -2. So we can make the the one-sided limit statement shown on your screen. On the other hand, if we're on this function, as our x value approaches -1 from the right, we don't arrive at -1, but we approach it, we see that our y value gets infinitely close to -3. And we can make the one-sided limit statement shown on the bottom of your screen. So the limit of f of x as x approaches -1 from the left exists, but it does not equal the limit of f of x as x approaches -1 from the right. So since they don't equal each other, we make the statement, the limit as x goes to -1 of f of x does not exist. Each of the one-sided limits exists, but the limit itself does not exist. Now, what if we're given the function shown here? Okay, well, the function f of x equals 2x minus 1, x less than 2, looks like what you see on your screen. If we want to graph the function y equals x squared minus 1, it would look like the parabola shown, but of course we're only supposed to keep the part to the right of 2 and including 2. So we end up having an open circle and then a closed circle right on top of it. So the function looks like what you see there. Now, as we approach from the left, we see that as x is approaching 2 from the left-hand side, y is getting infinitely close to 3. As x is approaching 2 from the right-hand side, y is approaching 3. So the two one-sided limits both exist, and they both equal 3. Therefore, the limit as x approaches 2 of f of x in that situation equals 3. Now let's use a graphing approach to evaluate the rational function shown. So what we're going to do here is we're going to graph the function y equals x plus 1 over x minus 4. You might recall that this function has a vertical asymptote at x equals 4. The degree of the numerator and denominator are the same, and the x's don't cancel out. So we have lead coefficient over lead coefficient, 1 over 1 equals 1, a horizontal asymptote at y equals 1. Okay? Now, we're going to graph this curve so we can find a couple of key points, or we can do our vertical asymptote, horizontal asymptote analysis, however we choose to do it. What we're doing here is we're finding that the point 3, -4 is on the curve we want to graph, and the point 5, 6 is on the curve we want to graph. So here's 3, -4, here's 5, 6, and we're going to treat our asymptotes like asymptotes, find our x and y intercepts, and we have a curve that looks like what you see there. Now, as we approach from the left-hand side, as x gets closer and closer to 4 from the left, we see that y shoots down to -infinity. And as we approach 4 from the right, as x gets closer and closer to 4, but from the right-hand side, and we trace along the function, we see that our y value shoots up to +infinity. So since those two limits don't exist, since the two limits don't equal each other, the two one-sided limits, we can say that the limit as x goes to 4 of that rational function does not exist. Now, I want to make a clarification here. Technically, I wrote a couple of bad things on the previous slides. In the last example, we expressed that the limits were equal to infinity and -infinity. Technically, that's not true. Nothing can equal infinity or -infinity. So a few slides ago, when I wrote this statement here, and I said that something was equal to -infinity, or on the next slide when I said something was equal to infinity, you could have just stopped right there and said that's impossible, and you would have been right. Okay? So nothing can equal infinity or -infinity. So one could immediately say, once you establish that one of the one-sided limits is going to infinity or -infinity, you could have immediately said, okay, the limit does not exist, because nothing can equal that. So then the test that the two one-sided limits equal each other couldn't possibly be true. However, now I'm going to read from this sentence right here, beginning with the word however. However, in this course, we're going to say that a one-sided limit can equal infinity or -infinity. Okay? And if we're seeking, but you can remember the following rule. If we're seeking the limit of a function as x approaches a real number, and if one of the one-sided limits is equal to infinity or -infinity, right away you can state the limit of the function as x approaches the real number doesn't exist. Okay? Once you get that one of the one-sided limits, quote unquote, equals infinity or negative infinity, you can say that the limit, if you're using a graphing approach, the limit as x goes to that number without a one-sided qualification, you can say that limit does not exist. So for example, you might write any of the following expressions. This is, we're going to see in a moment, sometimes we'll take limits as x goes to infinity or negative infinity. So you might write, if you're looking at one of these one-sided limits as x goes to infinity or negative infinity, you might write that that limit equals infinity or negative infinity. Or if you're looking at a real number, one-sided limit as x goes to a real number of f of x, you might write that those equal infinity or negative infinity, and that'll be acceptable in this course, even though technically it's not possible to say that. But if you find that when you're finding a limit as x goes to a real number, if you find that one of the one-sided limits is equal to either infinity or negative infinity, you can right away say, as I said a few minutes ago, that the limit as x goes to that real number of f of x does not exist. Okay? Now, sometimes you'll get a limit that can only be approached from one side. So sometimes we'll come across a limit that can only be approached from the left or the right. The most common type of limit of this form is when we seek to find the limit of a function as x approaches infinity or as x approaches negative infinity. If you want to evaluate the limit of a function as x approaches negative infinity, you can only approach it from the right. So for instance, imagine our xy axis. If I'm saying to you x is approaching negative infinity, that's way out here to the far left. Well, I can't be to the left of negative infinity. I can only be to the right of negative infinity. So I can only approach negative infinity from the right. And similarly, I can only approach positive infinity from the left. Positive infinity is to the far right. I can't be to the right of positive infinity. I can only be to the left and approach from the right. So it's something you'll get used to as you do a few examples. So let's say we wanted to use a graphing approach and evaluate the limit that you see there. First thing we would do is graph the function, y equals negative x plus 2. And then we would say, where is y going as x goes to positive infinity? Well, we can sort of tell intuitively we can only be approaching this from one direction. There's no way we can do it two one-sided limits here. There's only one direction you can approach positive infinity from. So we approach from the left, and we see that as we approach as we approach positive infinity from the left, our y value shoots down to negative infinity, and we can make this statement. Okay. What if we want to evaluate the limit as x goes to negative infinity of 1 over x plus 3? Well, what we'll do is first we'll graph the function y equals 1 over x plus 3, however you see fit to do that. Now, what we're now going to do is we're going to say, okay, x is going to approach negative infinity, but you can only approach negative infinity from one side. You can't approach from the other side. So we'll say the limit as x goes to negative infinity of 1 over x plus 3 will equal whatever the one-sided limit is as x is going to negative infinity from the right. And so what we do is we say, well, as the value of x keeps getting closer and closer to negative infinity, the magnitude of that denominator keeps getting huge. 1 divided by that magnitude keeps getting small, and our limit actually equals 0. So just think about it. If we graph that curve infinitely far to the left, we would see that our y values would keep on getting closer and closer and closer to 0. They'd get infinitely close to 0 if we kept on moving to the far left. Now, sometimes people want to say that the limit as x approaches negative infinity is infinity because they think as the y value will always be increasing, but that's not the case. Again, where our y values, this isn't a curve that goes up like this. This is a curve that's skating always below a particular horizontal asymptote. So the limit as the x approaches negative infinity is 0. It's not positive infinity. Y is not getting infinitely high there as we approach negative infinity from the left. So what we see is that horizontal asymptotes operate like limits. Now let's use a graphing approach to evaluate the limit as x goes to infinity of sine x. Okay, as x goes to infinity, we graph the curve y equals sine x, and as x goes to infinity, we see that first we're going to a y value of 1, and then a y value of -1, we're at a y value of 0, we're at a y value of 1. We're going to keep on going up and down below -1 and 1 forever, our y values. Okay, so therefore there's no one value that we can say the function is approaching as x approaches infinity. So therefore we're going to say the limit as x goes to infinity of sine x does not exist. Now let's use a graphing approach to evaluate the limit as x goes to 2 of square root of x minus 2 plus 3. First, what we're going to do is we're going to graph it. And you can tell right away you can't approach an x value of 2 from the left because the function doesn't exist. There's nothing out here that we can approach from the left. There's no path. There's nowhere for us to be. And that's because the domain doesn't contain any x values less than 2. Okay, so that one-sided limit does not exist. You might be tempted at this point to say, oh, okay, since that one-sided limit doesn't exist, we'll say the limit as x goes to 2 overall does not exist. But this is one of those exceptions to the rule. In this specific circumstance, when the function is not defined at all on one side of the x value in question, but is only defined on the other side, we focus solely on the side on which the function is defined. So we're going to approach an x value of 2 from the right. When we do that, we see that our y value is getting closer and closer to 3. And since that's the only direction from which we can approach that x value, we'll state that the value of that one-sided limit is the value of the limit of the function as x approaches 2, and we will write that, what you see there. The limit as x goes to 2 of f of x equals 3.